Hello dear students, welcome you all. Students, now I am going to solve the last question of section C of the house examination question paper. That is question number 7, right? You can see here the question number 7 was starting from Bose-Einstein energy distribution law, drive Planck's law of black body radiation. Clear? So this was the question. Here we have to drive this Planck's law by starting from Bose-Einstein energy distribution law, right? So what was Bose-Einstein energy distribution law? I'm coming to Bose-Einstein energy distribution law that was given to you. It was Ni upon Gi is equal to 1 upon e raised to power alpha plus beta ei minus 1. So this was Bose-Einstein uh, distribution law, right? So we have been asked here to drive Planck's law from starting here, right? You have not to drive this law for driving Planck's law. It is not asked here, right? So now I'm going to start driving this Planck's law. So actually Planck's law, right? Planck's law was derived by using Bose-Einstein statistics. Before driving Planck's law, we will make certain assumptions, right? We are applying here Bose-Einstein statistics. We know very well that Bose-Einstein statistics is applicable to identical and indistinguishable particles, right? Which have either zero or integral spin. So here in this particular case of black body radiation, we can treat that the black body radiation is basically what? It is basically a collection of a large number of photons, each having energy E is equal to h nu and momentum P is equal to h nu upon C. So here we have to make this assumption that this black body radiation is nothing but it is a collection of a photon gas. We will call it as photon gas, right? We will treat this collection of large number of photons as a gas molecules, as we did in the case of Maxwell-Boltzmann statistics. But remember, here photons are totally different from the classical gas molecules because they are identical and indistinguishable. They are quantum particles, right? So one thing is that. Other thing is that we have to consider that this photon gas is under thermal equilibrium. Under thermal equilibrium means no energy is added to this system or no energy is taken away from this system. It means that the total energy E of the system is constant. Clear? The container in which this black body radiation is contained is fully thermally isolated, right? And there is no loss of energy when the photon gas undergo collisions with each other as well as collisions with the walls of that container. This is the assumption, right here. So this is one assumption. Other assumption is that in this particular case, the photon number, right, that is n, it is not constant. This is very, very important. Clear? Clear? This is not constant. Clear? Why? Because we know in case of this photon gas, to two photon of energy E1 and E2 can combine to give a photon of energy E. Similarly, the reverse thing can also happen. A photon of energy E can convert into two photons of energy E1 and E2. So it means the total number of photons is not constant. It means if n is not constant, it means summation of ni is, we can say, it is not constant. It means summation of dni, that is not equal to 0. Clear? That we have did while we were driving the distribution law. While we are driving the distribution law, general law, this we have taken here in this case alpha. This alpha is involved for multiplication with this. You might have remembered that we ultimately what we do in this driving this relation, we multiply this relation by alpha, right? So it means alpha is going to be dropped from here. Alpha will not be used because this number is not a constant, whereas as the total energy E is constant, so we can write summation of EI uh, Ni is equal to constant. Clear? It means summation of EI dNi, that is equal to 0. This thing is constant, and this condition is valid, right? So this condition is associated with what? It is associated with the Vita, right? So it means in this equation, this Bose-Einstein distribution law, alpha term will get dropped, right? And now we are making substitution, these two substitutions in this equation, right? So then after we will write it as now it will become Ni is equal to, I can write Gi here, Gi upon e raised to power uh, beta Ei minus 1. We know we have did in the case of Maxwell-Boltzmann statistics that beta is equal to 1 upon kt. Clear? So I can put the value of beta here. So it will become e raised to power minus ei upon, not minus, sorry, plus ei upon kt. Clear? So this is what this equation becomes. Bose-Einstein distribution law becomes when we apply the condition that we discussed earlier. Right? Now, let's assume that this Ni represent the number of photons that have energy in the range of frequency nu minus 1 by 2 to nu plus 1 by 2. It means this is the range. So the energy in this range is obviously h nu, because the range is nu minus 1 by 2 to nu plus 1 by 2 means the difference is only of 1, right? So I can now write this equation. Clear? This equation as n nu d nu is equal to g nu upon e raised to power. Now ei is what? H nu. We are taking the energy interval as h nu upon kt minus 1. Clear? Into d. So we have converted this equation now into this one by applying the condition that we are taking the energy interval h nu. Clear? You know very well that when we are making the distribution of particle in different compartments, compartments are of different size, right? And then ultimately these compartments are divided into cells of equal size. This was the article that we have discussed in the first chapter. So here we are taking the interval. This is the interval. This is first, second, so on. So this is the interval. So we are taking the interval h nu, right? So when we are taking the interval h nu, so then this equation n nu d nu This gives us the number of photon in the frequency range of nu to nu plus d nu when I multiply it by d nu on both the sides, right? Now, we are going to convert this relation into momentum relation. So for that, first of all, we have to write down the number of phase space cells in the momentum space Gp dp. Clear? This what is GPDP? GPDP is giving us the number of phase space cells in the momentum range of P to P plus dP. We know very well, we have discussed in the class also, that how we can calculate this. This is simply can be calculated by calculating the volume in the position space multiplied by in a momentum space. Volume in position space, volume in momentum space divided by volume of a cell, right? So obviously volume in position space will be what? It will be dx dy dz b, right? What is the volume in momentum space? Now it is very important here, all the phase space cells in the momentum space in the range p to p plus dp will lie within a sphere, right? Within the sphere, this is the sphere. So all the points in the range of p to if I took this, this is dp, right? So we are actually, what we are doing, we are calculating the number of points in the momentum space in this range, right? So it is obviously, we know from the knowledge of mathematics, it is 4 pi p square dp. So b into this volume in momentum space will be simply 4 pi p square dp, right? And divided by what? Volume of a cell in quantum physics, minimum volume, h cube, right? So this gives us gp dp, right? So it becomes, gp dp becomes, right? So this is the given number of you know uh, phase space cells in the momentum space, right? Now it is very important that we have taken here photons as indistinguishable particles, but we know very well that we can have two type of photons, one with one type of polarization and other with opposite type of polarization. We can say one right circularly polarized and other left circularly polarized, because photon can have two type of polarization, right? Two type of spin, right? So it means we have to multiply this number of phase space cell in momentum space by 2, because two type of photon can exist there. So we are going to multiply it by factor 2 to accommodate all the possibilities. So here it will become, in that case, if I multiply it by 2, then the 4 will get replaced by 8. Clear? So here it will become 8. Now it becomes 8 pi b p square upon h cube dp, right? Gp dp. So now I'm going to convert this expression, because here in this equation, in this particular equation, what we require, g nu d nu, number of phase space cells in the frequency range of nu to nu plus d nu. But this expression is in the range of momentum. So we have to change momentum to the energy. So we know in case of photon, P is equal to h nu upon c. So dP is equal to h upon c d nu. So we can put these things here. So when you will put these things here, you will get g nu d nu is equal to 8 pi b upon h cube. P square means h square uh, nu square upon c square. H square nu square upon c square into dp. Dp means h upon c d nu. So what it becomes ultimately? It becomes uh, g nu d nu becomes 8 pi b as it is upon here you will get these two terms h cube h square h c cube because c square c and you are left with the nu square, right, d nu. This is equal to what? This is equal to g nu d, right? Now we are going to submit put this value in this equation, right, in this equation, n nu d nu. So you will get n nu d nu is equal to 8 pi b upon c cube nu square d nu into 1 upon e raised to power h nu upon kt minus 1. Clear? So what I did, I put this value in this equation. Clear? G nu d nu value from here in this equation. Then I got this expression. Now what is this? This formula is giving us the number of photons in the frequency range of nu to nu plus d nu, right? If I multiply this relation with what? With h nu. So it will give us the total energy in this range. Clear? Total energy in this range. So, and if I divide this by B, total volume, then what it will give? It will give us the energy density. Clear? Of the radiation. So, if I do it, then I can write it is E nu d nu. What is it? It is from here. Energy density of the radiations in this frequency range. So same thing I have to do here. I have to multiply it by h nu and I have to divide it by b. So b got cancelled with b. So it will become 8 pi h nu cube upon c cube into d nu upon e raised to power h nu upon kt minus 1. Clear? So this is what we were looking at. This is now the energy distribution, energy density of the radiation in the frequency range of nu to nu plus d nu. So this is this formula that we have derived starting from here. This formula is called Planck's formula. It gives us the energy density of the radiations. E nu d nu is equal to 8 pi h nu cube upon c cube into d nu upon e raised to power h nu upon kt minus 1. Right? So this is the expression in terms of frequency, right? Well, it was the uh, Planck's formula in terms of frequency. Clear? If we want to convert this formula in terms of wavelength lambda, then we can convert it in terms of wavelength also. I have simply asked you to drive this formula. You can see here. Starting from Bose-Einstein distribution law, drive Planck's law of black body radiation. So I have not asked you to drive it in terms of frequency or in terms of wavelength. So even if you have derived this formula up to this equation, then you are getting the full marks. But you can convert this formula into the formula in terms of wavelength, right? So we can do it. We know the relation between uh, nu is equal to C upon lambda. So d nu is equal to minus C upon lambda square into d lambda. So if I put these values here in this expression, then this formula will get converted into the formula in terms of wavelength. So it will become E lambda d lambda is equal to 8 pi h upon c cube. Nu cube means in the formula we have nu cube. Nu cube means it means c cube upon lambda cube into what it was uh, d nu upon e raised to power h nu upon kt. So it into it will become into minus c upon lambda square d lambda upon e raised to power minus not minus sorry plus hc upon lambda kt minus 1. Clear? So when you will simplify this, some of the terms will get cancelled and some terms will get multiplied. E lambda d lambda, and you will take the modulus of it because there is negative sign, so you will take the modulus of it. Then it will give you 8 pi h c upon lambda power 5, and so it was 8 pi hc upon lambda power 5 into d lambda upon e raised to power hc upon lambda k t minus 1. So this is the expression in terms of wavelength, right? E lambda d lambda is equal to 8 pi hc upon lambda power 5 d lambda upon e, right? So even if you have derived the Planck's formula up to this relation, then I have gave you the credit. But if you have did it, then it is excellent. You are able to convert this formula, Planck's formula, into the formula in terms of wavelength. So this is all about it. Now we have finished all the questions. This was the last question, Planck's law, right? For the black body radiation that we derived here, right? So now in the next lectures we will start discussing the next problems of statistical and thermal physics, right?